7.2 is on infinite sequences and the factorial. And so we're going to start this section by reviewing some notation, some symbols and things that you have learned throughout your mathematics career. We're going to review what they are and what they mean, and then we're going to tie that back into calculus, obviously, when we're going to start talking about whether or not a sequence converges or diverges. So, just as a reminder, a sequence is a list of numbers in a defined order. Each value has a specific location. We define this typically using a sub n, a sub 1 being the first term, a sub n being the nth term, a sub n plus 1 being the term after the nth term, and we can define it in that way. And in this notation section, you'll see a bunch of different forms which really all mean the same thing. A sub n from n equals 1 to infinity. You could list them off in set notation. And really in calculus, we're not incredibly particular about how we notate using any of these different forms. You should just be able to recognize them all and see or interpret what they mean. So for example, the expression 3 over n plus 1 in set notation would be the same as 3 over 2, comma 1, comma 3 over 4, dot, dot, dot. A couple things I do want you to notice. These ellipses, yes, there do need to be 3 of them. You'll notice there are 3 terms, then there is an ellipses, and then there is the general term, which basically tells you how the rule works. And then that is followed by another ellipses, meaning that it is infinite and it goes on forever. In calculus, we're really never going to be talking about finite series as you did in Algebra 2 and pre-calculus. Finite is pretty boring. In calculus, we want to talk about what happens as we go to infinity. So we're going to focus on sequences in this lesson, and we're going to tie that into series in the next few lessons. Another thing that we need to review, in case you have forgotten, is the idea of what is a factorial. A factorial is that exclamation point. Exclamation point does actually mean something mathematical. It means that we multiply that number by all of the numbers, all of the whole numbers below it. So n factorial is the same thing as n times n minus 1 times n minus 2 and so forth all the way down to 1. So for example, 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1. And then the last review idea we're going to talk about here is the idea of something being recursive. Recursive meaning it uses the term before it. So a sequence whose terms are defined by the terms that precede it are called recursive sequences. An example of this is the Fibonacci sequence, in which each term is the sum of the 2 previous terms. So here is the definition for the Fibonacci sequence, and it actually tells you what the first and second term are, since the rule uses those 2 terms. So the Fibonacci sequence is 1, comma 1, then you add those 2 terms together to get 2, then you add these 2 terms together to get 3, 5, 8, and then you can see AK minus 1 plus AK minus 2, comma, dot, dot, dot. And recursive rules you actually learned about briefly in Algebra 1, where you identified an arithmetic or a geometric series, and you basically said to find the next term you multiply by 3, or to find the next term you add 2. Those were recursive rules, and it's that idea of explaining how to find the next term using one or more previous terms. So what I want you to do, just to sort of check in with your previous skills, is I want you to pause this video, and I want you to work on these 3 practice problems here. They should be a review, they may not be, but I want you to see how far you can get, and then you can unpause the video and walk through them with me. All right, here we go. Number 1, we're simplifying some factorials. So the top of this factorial, or this fraction, could be written as n plus 1 times n minus 1 times n minus 2 times n minus 3 factorial. And I want to get there so that when I rewrite the denominator, these can divide out. So this would leave me with n times n plus 1 times n minus 1 times n minus 2. And I just switched the order because I like to have my just n term in the front. But obviously this is multiplication, so that order is pretty much irrelevant. So you should be able to look at something like number 1, seeing those factorials, and actually simplify it as much as possible. Number 2 is really assessing, can you look at a rule, or can you look at a pattern and write the rule? So this rule would be a sub n is equal to, the first thing that I notice is that this is an alternating pattern, and to make a pattern alternate, as you should recall, you can use -1 to the n. And then the rule, what's happening in the numerator is we're increasing by 1, but we're starting at 3. So I'm going to write n plus 2 over what's happening in the denominator. I'm raising each term to the power of 5, or 5 to the power of each term number. And you could leave it just like this. Unless otherwise indicated, you should assume that a sequence starts with n equals 1. If you wanted it to be differently, you would need to specify that in the problem. But I want this to start at 1 because I want this to be negative and I want this to be 3 over 5. So again, unless otherwise specified, you're assuming that a pattern starts at 1. If it's specified it starts differently, then it will. And then the last part, number 3, is just asking us to find the first 3 terms, and it tells us here to start when n equals 1. So a sub 1, I'm going to show a little more work than I think you would need to here. It's going to be 1 factorial minus 1, which is 0. A sub 2 is going to be 2 factorial minus 1, which is 1. A sub 3 is going to be 3 factorial minus 1, which is 6 minus 1, 5. Couple ways you could write this. You could use set notation 0, 1, 5. I don't have to say that this goes on forever because it specifically just asked me what are the first 3 terms. You could also just write it as 0, 1, 5. It would be okay if you showed that it was infinite and you added that on there. That is also fine. We're not really particular, especially when we're talking about sequences, because really we're just laying the groundwork here to move into series, which we'll get into the notation required for that when we get there. Okay, the next thing I want to show you is how you can actually use your graphing calculator to look at sequences. So I'm going to have you pause the video, grab your graphing calculator. And once you have your graphing calculator, you're going to hit mode. You're going to go down to where it says function, pair, polar, sequence. You're going to go over to that sequence mode. Remember, you're going to need to take it back out of this, especially if you're taking another science class. And oftentimes, even in this class, you need to make sure, I would actually say when you're done with what we're about to do, put it back into function mode. But for right now, we're going into sequence mode. Then you can exit out of there. Then I'm going to have you go into the y equals mode, which should look very, very different if you're in sequence mode. You're going to see this little weird cursive looking n min. You're going to see a little /u with a little n. On that second line where it's asking you for the function u of n, you're going to go ahead and type in what you see on number 4. You don't need this set notation bracket, so you can just type 3n over 1 plus 6n. Make sure you're using parentheses to tell your calculator what is being grouped together. And then if you hit second table or second graph, you will see these values in a table. And I would just go ahead and type in 1, 2, 5, 10, 100. See what's happening as you're inputting different values. See what's happening on the right-hand side in the function mode. Our goal here is to identify as the numbers are getting bigger, does it seem like it has a limit? So as we're going closer and closer and closer to infinity, does it seem as though it is approaching a particular value? So go ahead and pause the video, test this out on your calculator, and then unpause the video and see how you did. So the more I look at these values in my table, the more it looks like we are converging to 1/2. It looks like the values are getting closer and closer and closer. 0.46, 0.48, 0.49, 0.499, etc. Getting closer and closer and closer to the value 1/2. And actually, if you look at the graph of this as well, it's much harder to see. But you can see that they are getting closer and closer and closer to some number. It's definitely harder to identify what that number is, which is why I prefer to use the table mode. All right, I want you to do the same thing for numbers 5 and 6. So pause the video and analyze the behavior of what's happening with those two different rules, a sub n rules, and see if they are converging towards any one value. So I've typed in my a sub n into my y1. I'm in the table set mode. I'm looking at when n is 10, when n is 100, when n is 1,000. I see 2.1, 2.01, 2.001. So it does kind of look like this, and we're not mathematically computing anything. We're just analyzing behavior. It does look like this limit is converging to 2, or it does look like the limit of this rule, so to speak, is 2. Pause the video and look at number 6. So I've typed in my a sub n in my y equals for number 6. And when I go into my table set, the numbers I've been using, I'm actually getting some errors. So I see when I plug in 2, I get 2.2, 5, I get 2.69, 10, I get 3.868, 100, it gives me an error. So I want to see what's happening, let's say, at 20, since 100 gives me an error. At 20, I jump up to 9. At 30, I jump up to 24. Let's see if it'll let me do 40. At 40, I jump up to 68. So this is growing, and it doesn't look like, I know once I get to 100, it tells me there's an error. So I'm having some issues here. So I'm going to assume that this probably diverges. And if I actually take a look at the graph, I can see that it's growing, and it doesn't look like it's converging to any particular value, or it doesn't look like it is approaching any particular limit. So it is possible, just like any other function, that as we go to infinity, that function is actually going to infinity, which we would say in this case that it diverges. All right, before we put our calculus spin or look at this through the lens of calculus, I want you to pause the video and work through 7 and 8. See if you can list the first 5 terms of each sequence. Remember that you're plugging in values for n. And here are the first 5 terms. So a couple things to notice. Again, I'm not going to be real particular about notation. You could definitely have an ellipses here. You could definitely have written them without using set notation. What I'm really checking on right now is, do you understand the math? I'm not focused on notation because, again, sequences are just leading us to the bigger picture that we're going to be talking about for the next 2 units, which is series. So check over those 2 problems and then we're going to move on. So we just used a graphing calculator to analyze the behavior of a sequence as it is approaching infinity. And we just looked at that graphically and we looked at it using a table, but what we actually are going to do is think about this as if it were a limit. We can apply everything that we know about the limit of a function to the limit of a sequence. It behaves in the same manner. So the terminology and the analytic approaches are very, very similar. The limit as n approaches infinity of a sub n could be equal to a number. And if it is equal to a number, then we would say that that limit exists. That could also be written as a sub n approaches L, or a sub n approaches L as n approaches infinity. But really, we're saying that that limit does exist. If that limit exists, we would say that that sequence converges or is convergent. So that would be like the first 2 examples we looked at, numbers 4 and 5, where they were both approaching a value as we approached infinity. As opposed to the last one that we looked at, where it was actually divergent. It wasn't approaching one particular value, or it may be approaching infinity or negative infinity. So we would say that that does not exist, or we would say that it diverges or is divergent. So the moral of the story is we're going to treat sequences in the same way as we treat functions in terms of finding the limit and seeing what they are approaching. So let's look at this example. Find the limit of the sequence b of n, which is n over 1 minus 2n. So we're going to take the limit as n approaches infinity of n over 1 minus 2n. And just using basic rules of limits, right? I have a polynomial over a polynomial. So I can just divide the coefficients in front of the leading term, or the leading coefficients. That's going to give me negative 1/2. So this sequence converges because the limit exists. Okay, let's look at number 9. So we're going to take the limit as n approaches infinity of 3 plus 5n squared over n plus n squared. Again, looking at this, they're both degree 2 polynomials, so I can divide the leading coefficients. That's going to give me 5 over 1, or 5. Therefore, this sequence converges. Number 10, the limit as n approaches infinity. I'm going to rewrite this as 3 to the n over 7 to the n. This limit is going to be equal to 0 as n approaches infinity. The bottom is growing faster, so this is slow, this is faster. So that limit is 0. Therefore, we can say that this sequence converges. So again, we're using this idea of a limit to decide, does this sequence converge or diverge? Why don't you go ahead and pause the video and work on 11 through 14. And if you get stuck, just skip one and then unpause the video and we can work through them together. Number 11, the limit as n approaches infinity. And I'm going to go ahead and make that a positive exponent. So 1 over e to the power of 1 over root n. Well, as this goes to infinity, the exponent here, 1 over the square root of n, that's going to 1 over infinity, which is going to make this 0. So 1 over e to the power of 0, this limit is just going to be 1. Since this limit is equal, or exists, since this limit is a value, we can say that this sequence converges. On number 12, your understanding of factorials is going to come into play. You need to rewrite this as the limit as n approaches infinity of 2n minus 1 factorial over 2n plus 1 times 2n minus 1 factorial. So those are going to divide out. The limit as n approaches infinity of 1 over infinity is going to be 0. Therefore, this sequence is also going to converge. On number 13, we're going to use some logarithm properties to change that denominator to be natural log of 2 plus natural log of n. So think about what's happening here. Natural log of 2 is just a constant value. So we're looking at what's changing as n approaches infinity, and the only thing that's really changing as n approaches infinity is this stuff here. And that stuff is changing at the exact same speed. So as n approaches infinity, the natural log of 2, which is just some small number, is becoming irrelevant. So the limit as n approaches infinity of natural log of n over basically nothing plus natural log of n, this is really just going to be equal to 1. The numerator and the denominator are basically changing at the exact same rate. Therefore, this is going to converge. And if you don't believe me, which I know, it's sort of hard to think about that, think about it this way. As n approaches infinity, let's look at what's happening. So let's actually look at the limit. Let's put a limit here. As n approaches infinity, let's factor out natural log of n over natural log of n. In the numerator, that would leave me with 1, right? I want to distribute and get back here. In the denominator, that would leave me with natural log of 2 over natural log of n plus 1. And what's happening as n is approaching infinity? As n is approaching infinity, this is going to 0 because the top is a constant and the bottom is going to infinity. Slowly, because natural log grows slowly, but it's still going to infinity. So this is going to 1 over 1, right? This is changing at exactly the same rate. So we're going to get that that limit is equal to 1. And lastly, number 14, the limit as n approaches infinity of sine of n. Well, this limit doesn't exist, right? Sine is oscillating between -1 and +1. So the limit doesn't exist, which means that this sequence diverges. All right, we're going to wrap up with just a little tiny bit more vocabulary, which should mostly be review about monotonic and bounded sequences. So a monotonic sequence is a sequence that is either non-increasing or non-decreasing. And what I mean by that is it's either always increasing or it's always decreasing or it's always constant. So monotonic meaning, mono meaning one, only one behavior is happening. So it's always increasing. For example, 1, 2, 3, 4, 5 would always be increasing. Or it's always decreasing. 5, 4, 3, 2, 1. Or it's always constant. So that there is actually a third option. It could just be that it's neither increasing nor decreasing the entire time. It could just be constant, like the sequence 1, 1, 1, 1, 1. That also doesn't have a change in behavior. So monotonic, always increasing, always decreasing, or always constant. But an easier way to remember that is there is no change in the type of behavior that's happening. The other word we're going to talk about is new, and it is bounded. A sequence is bounded when there's some number that every term in the sequence is less than or equal to, and a number that it is greater than or equal to. Basically, a sequence is bounded when it has an upper limit and a lower limit. Every term in the whole sequence falls between two numbers, this number and that number. If a sequence is only bounded in one direction, we actually could say it's bounded above by some value, or that value n is the upper bound. Or we could say that it's bounded below by some value, or that value is the lower bound. It is only bounded if both are true. And these terminologies, monotonic, bounded, upper bound, lower bound, those are just terms to help us understand the behavior of what's happening, which helps us analyze what's happening a little bit better. So number 15, 16, and 17 are asking us to determine if it's bounded or monotonic or both. So looking at number 15, let's just look at what is happening with the terms. The first term here, if I plug in 1, would be 2. The next term, 4. The next term, 2. The next term, 4. So it's alternating between 2 and 4. So it is not monotonic. It's getting bigger, it's getting smaller. It's getting bigger, it's getting smaller. But it is, in fact, bounded. It's bounded above by 4, and it's bounded below by 2. It never gets higher than 4. It never gets lower than 2. So it is bounded. Go ahead and pause the video and work on 16 and 17 on your own. Okay, number 16. Let's look at the terms here. I have 1 4/3, 6/4, 8/5. And it keeps growing. And it's growing pretty slowly. This is definitely always getting bigger. It's an increasing, if I thought about it as a function, it's an increasing function. Or I guess I could just say it's an increasing monotonic sequence. Is it bounded? Well, it's definitely growing, but each time it's growing a little bit slower. And if I think about this, if I think about the limit of this, that limit is 2. It does look like it's getting closer and closer and closer to 2. So this is bounded. It's bounded below by 1. It's bounded above by 2. So I could say that it is bounded. Number 17 is monotonic. If I look at the terms, 1/2. 4/3, 9/4. So it is monotonic. It is an increasing sequence, monotonic. And is it bounded? Well, it's not growing. Thinking about, if you thought about the limit here, n squared over n, that's going to infinity. So it's not bounded. So you could say not bounded. You could say unbounded. Or if you really wanted to, if you wanted to be as specific as possible, what you could say is that it's bounded below. It's bounded below, not above, but it is bounded below. It never goes below 1/2. 1/2 is the smallest term since it's increasing everywhere after that, and all of these things would be accepted. You can't say bounded because you have to actually have the word below there to specify that it's only bounded up below, but you could also just say that it's unbounded or not bounded. All right, last question, number 18. If a sequence is bounded and monotonic, what can we say about its convergence? So go ahead and pause the video and think about what those conditions mean, and then see if you can come up with an answer to that question. All right, bounded, meaning it has an upper and a lower bound, so it's trapped between two numbers, and it has a single behavior since it's monotonic. So what does that say about convergence? It is always going to converge. So key concepts from this section, reviewing some vocab. You should be comfortable working with factorials. You should know what recursive rules are. You should be able to identify a pattern and write a rule. All of that is review from Algebra 2 and Pre-Calc. The new stuff, the calculus stuff, applying what we already know about functions to sequences so that we can take the limit, so that we can decide if a sequence converges or diverges. And a sequence will converge if it has a limit. If the limit exists, then the sequence is converging. The last thing we talked about were a little bit more vocab, monotonic and bounded. Monotonic meaning it's always increasing or decreasing or constant. Bounded meaning it has both an upper and lower value. So if you have any questions, make sure to write them down, and I'm looking forward to supporting you on this in class. Thanks for listening.